implemented a complete variational autoencoder or VAE from scratch using PyTorch. I also built an interaction streamlit application to explore and interpret the learned latent space. The main goal was not only to train a generative model, but also to make the model behavior transparent and explainable through visual analysis tools. Okay, let us discuss about problem. Unlike supervised models, the map inputs to labels. Generative models learns the underlying data distribution. A VAE learns a latent representation of images and can generate a new samples by decoding points sampled from the latent space. For this project, I used Fashion MNIST and focused on three core objectives. The first one is correct implementation of the VAE architecture with the reparameterization trick and ELBO loss. The second thing is stable training with KL annealing to reduce posterior collapse. And the third thing is interactive latent space interpretation using a streamlit dashboard. Okay, coming to the architecture, the model has three parts. The first one is encoder. It is a convolutional encoder, takes a 28 into 28 grayscale image and outputs two latent vectors, mean vector mu and log variance vector log var. And coming to the second part, reparameterization trick. It allow back propagation through sampling. The latent vector is computed as z equal to mu plus EPS ILON into sigma, where epsilon is sampled from a standard normal distribution and sigma is derived from log var. And coming to the third part, a transposed convolutional decoder maps Z back to image space and reconstructs a 28 into 28 image. So the full data flows is input image to encoder, encoder to mu comma log var, from this to reparameterization, from this to Z, from this to decoder, and at last it reconstructed the image. Okay, coming to the loss function and training strategy, the VAE is trained using ELBO, which combines reconstruction loss and KL divergence. The total objective is loss equal to reconstruction loss plus beta into KL divergence. A common VAE failure mode is posterior collapse, where KL becomes near zero and latent variables are ignored. To mitigate this, I used KL annealing. Start with small beta, gradually increases beta to 1.0 over early epochs. This helps the model first learn reconstruction and then gradually regularize latent space. I also logged reconstruction loss and KL divergence separately at each epoch. Coming to the result and diagnostics, from training logs and generated plots, reconstruction loss decreases consistently. KL divergence remains active instead of collapsing to zero. I generated and analyzed training curves for reconstruction and KL loss, KL divergence per latent dimension, reconstruction examples with error heat maps. The KL per dimension plot helps detect inactive or dead latent dimensions. In this run, multiple dimensions remained active, indicating healthy latent utilization. And the coming to the Streamlit app demo, the Streamlit Explorer includes four main components. The first one is latent space map. It contains encodes test images, project latent means to 2D using PCA, displays class colored scattered plot. And the second thing is latent sliders. It is in this one slider per latent dimension, real-time decoding from user-defined latent vector, immediate visual feedback on generation behavior. And coming to the third thing is reconstruction viewer. In this, we can select any test image index. It shows original and reconstructed image side by side, and it displays absolute error heat map. Coming to the fourth point, KL per dimension analysis. It means KL computed per latent unit. It contains bar chart, highlights active versus weak dimensions. This makes the model interpretable and easy to explore interactively. And coming to the structure of this project is, the project is fully production ready. It contains Docker and Docker Compose setup, health checkup enabled, Streamlit service, trained checkpoints at models directory vae.pt, logged metrics as training log.csv in results directory, and required scripts for reconstruction and KL plot generation, and posterior collapse analysis report, and also automated verification script for submission checks. To summarize, this project combines correct VAE implement in PyTorch, stable training using KL annealing, strong interpretability through an interactive latent space explorer. This demonstrates both generative modeling fundamentals and practical machine learning application engineering. Thank you for watching.